All right, it is almost time. So if you did the second exam, they're here, you can turn them in. And then I have your first exam. If you did turn it in, I have it to hand back. And let me talk a little bit about these. So I've offered for you to get help if you need help, and I only have heard from a few students for help. And some of the things that were done on the take-home exam were just really off. So I encourage you again to reach out for help, even if it's just like, hey, will you look at this? Does this look right to you? Like anything, so that you don't turn something in and get it back and it's a 40, right? Because one of these may not hurt you, but eventually, if that keeps happening, it's gonna be hard to dig yourself out of that. So when you get these back, look through them. Some of them, I've got correct answers, but I'm not sure what you're doing. So I've asked you, hey, if you want full credit, talk to me, and I'll give you the points back. But you need to kind of explain what you were doing here. So. Also, try to work on, I want you to get things right. That's overall, I want you to get things right. But part of this is, you're Cal 3 students, right? Which means you've been through Cal 1, Cal 2. And so I expect a certain level of pride and just when you turn something in, it should reflect your, I don't know, what am I trying to say? It should be a reflection of you are a student ready to transfer out into a university and go compete with a bunch of other people who are trying really hard. It should also reflect that. I want to be able to read it. I was talking to one of your classmates about this. You should be able to go back and read this in a year and be able to follow what you were doing. So writing things like, okay, I'm finding the intersection of two lines. Here's what I'm doing, right? Just a bunch of correct things scattered all over the place. Yes, it's correct, but that doesn't help you communicate those ideas to me. So part of the assignment is getting the math right. The other part is you turning in something that you're proud of, that somebody is going to read this. And again, that's not something that maybe happens the first one you turn in, but as time goes on, they should get better and better and better. So it's something to work on, all right? So I'm going to pass these back. There's no grades visible, so no one's going to see your grades, so just pass it around, get yours out of here, and pass it around. I think the highest grade was 100. I think we may have had more than one. And I can say that the students who have seen me in my office, those students got A's on this test, the first one that was turned in. And that's because, we went through it, and they, it's like, yep, you're on the right track. So. I don't know what else to say. Do you all understand what I'm getting at? Yes. Syllabus. Check the syllabus. Yep, it's Monday through Thursday, 7:45 a.m. to 8:45, and then right after class today, I have a 20-minute break for lunch, and then 1 o'clock to 2, and then other days it's 12:45 to 2. I don't know. You have to check the syllabus. But yeah, so come by, and then also, how many of you have I talked to on the phone? Right? I've talked to several of you on the phone, and I felt like those were useful conversations. You have that as well. When I say on these tests, reach out for help. So if you can't make my office hours, now that just keeps coming. So here's the next one. This one's due next Wednesday. So it's not a whole lot of turnaround on this one, but there's only, how many problems? 3? 4 problems. So 4 problems. You've got about, 9 days or so to get it done. And I believe, if I remember correctly, I think I gave out too many of them. I believe, can I look at it real quick? I believe, if I'm not mistaken, that, everything on here we've already talked about. That's why I'm having it due next week, because I don't want us to get too far behind in terms of our mini exams. So in theory, you should be able to do that mini exam with everything we've talked about, not even including today. All right? Are there any extra mini exams? I want to give you all some hints. Are there any extras? Are there any others? That's it. Thank you. Got it. Okay, y'all paying attention? These are good hints. Here, do you want to test? That's the next one. That's due. Are you turning in?
Yeah.
Okay. Let me make sure I am recording. Did I hit record? Oh, wait. Yeah, I did. It's so hard to see that red dot up there. Roll the first exam. Do you want the first one back? All right, so some hints. Ready? So all of these problems are 10.7 through 10.8 out of the book. So there's only 2 sections of material. When you're asked to find the maximum speed, you need to know what the speed of a particle is if it's moving on a curve, right? Speed and velocity are 2 different things. So make sure you make that distinction. If you're trying to figure out maximum speed, right? Maximum speed, you're trying to find the maximum of speed, which is, velocity is a vector, right? Speed is a scalar. So you're trying to find the maximum of some sort of scalar function, which takes you back to Cal 1. How do we find maxes and mins? Well, here we want a max, but how do you find the maximum of something, right? Well, that's what you're going to have to figure out. How do you find the maximum of a scalar function? For 2, 2 is just going to suck because you've got to do an antiderivative, and the antiderivatives of those are going to require some stuff from Cal 2. Like, you're going to have to dig into your integral techniques, integration by parts, other things like that, trig integrals. So I give you acceleration, and I give you some information about the velocity and the position, and you go backwards to get your position function. We did examples like that in class, but it was a very simple antiderivative. These antiderivatives are going to be a little more tedious. And then once you do that, you find the distance from the particle to some plane. That should be the minimum distance. Where it says find the distance from the particle to the plane, it should be the minimum distance, not just distance. Okay, for number 3, 3 always gets people, all right, because they don't know what they're supposed to do. But I gave you a big hint about this last class. You've got this curve, right? R of t. It says space curve. It gives you the position of a particle at each point in time. I tell you that the particle starts at, that's supposed to say the point, not he point, at the point 0, 0, 0. So you've got this particle starts at the origin, starts moving along this curve, right? And it moves a distance of 4 units along the curve. Where is it now? So I'm telling you, this thing starts at the origin, it moves along the curve, and that distance it travels along the curve is 4 units. And I want you to tell me exactly where it is, the point, the x, y, z coordinate of where it is now. Okay? So you need to think about, what have I given you, right? I gave you the starting point and I gave you something else, but what is that? It's a rhetorical question, right? Think about what that is. 4 units. And then if you're confused, think about the titles of these sections, right? Or titles of the topics in these sections. Okay, last one. You're given the position function. Notice there's a constant in there, a, right? This is the vector function for a helix. It says find the maximum or largest possible curvature and determine the value of a which yields that maximum. So you need to figure out what the curvature is first. What's the curvature of that vector function? We're going to do an example today. We only did one last time. We're going to do one more curvature problem. So you've got to figure out what the curvature of this vector function is. And the problem is it has a constant in there, a. So your answer, your curvature is going to have a in it. And I'm asking you, what value of a makes that curvature the largest it can be? And believe it or not, this is going to take you back to Cal 1 again, where you're going to have to try and find the maximum of something. So you need to show it to me on problems 1 and 4. Both those problems require you show a maximum of something, and you need to actually show it. You can't just be like, oh, I went and graphed it on Wolfram, or on Desmos. You need to show me how to find the maximum. They're not hard functions to find maxes of, but you need to show the actual technique. All right? So I'm giving you all quite a bit of a hint there, I think. See how it goes. Reach out, like I said, if you need help. I do want you working alone on this one again. See how it goes. All right? All right, let's get down to business. Let's get back into curvature, right? We were talking about curvature last time. Everybody who's turning in the exam 2 has turned in? Yes? All right. So curvature. Curvature measured like the curve, how much the graph curves, right? And I am going to write down the 2 formulas we have here. The first one, I think we used this one last class, right? When we did the example, it's really kind of a crazy formula because it's the magnitude of the derivative of the unit tangent vector function over the magnitude of the derivative of the vector function. And then the other formula, which we could have used, but we were not in 3-dimensional space, so we decided not to, was this one. And we are going to use the second one now, just so you can see it. All right, that marker's on its way out. All right, those are the 2 formulas for curvature. And now let's do our example. So here's the vector function I want us to do. Right there. I'm going to write it down, then I'll clear the screen up here. So we're doing r of t equals t 1 plus t squared. Something else I have to say about the take-home, and I talked to some of you already about this, is that these take-home exams, I know that there's a feeling that students get in this class where it's like, it's hard to make yourself go do the homework because it's not part of your grade and you've got these exams to work on. But if you're missing the foundational ideas, it makes these exams really hard. Because if you don't understand, you need a starting point and a direction vector to define a line, or to define a plane, you need a point and a normal vector. If that sort of thing is like a mystery to you, then answering these questions can be really tough. So try and keep up with your homework. All right, try to, and don't be surprised if you're not doing your homework if you're lost. Like that wouldn't be a surprise to me to hear that. So I know it's a lot of work, but I mean, this is Cal 3, right? I mean, I would. All right, curvature. We can use this one because it involves a cross product, and that's in 3-dimensional space, so cross products are valid, right? So let's do it. I need the derivative, I need the second derivative, and then I need some magnitudes, right? And I need to do a cross product. So let's figure out what the derivative is. What is the derivative of that vector function? 1, 1, and 2t, right? The derivative of a vector function is another vector function, right? Let's do a second derivative because that formula requires second derivative. 0, 0, 2. Very nice. And I'm going to need to cross those, right? Let's cross those. So this is all just like scratch work. If I take that derivative and I cross it with the other one, let's just do the cross product. And I wrote them like this so it'd be easy for me to do the cross product, right? How do we cross 2 vectors? Hey, when you take 2 vectors and cross them, you get a vector that is perpendicular to both of the ones you started with, right? Okay. Again, there's foundational ideas here. So when I take this vector and cross it with this vector, I should get a vector that is orthogonal to both these vectors. That's kind of irrelevant. I'm just pointing out that's the main property of a cross product. So let's go ahead and cross these. So how do we do it again? Cover up the first one, right? And then do the determinant here. So 2, take away 0, right? So just 2. And now negative, now let me do the determinant of the other one. So here, cover up, 2, take away, nothing again. So negative 2 will be there. And then last one, I cover up this and I get 0. So that's the cross product of the 2 derivatives. So 2, negative 2, 0. Good? Yes?
I'm sorry, what is K again?
Curvature. The curvature. It's telling you how much something curves. If you go back to last class, we did an example with the unit circle, and we found that the curvature was constant, which you would expect on a circle, right? If you're moving around a circle, you're curving at the same amount all the time. Here, we're on a different sort of curve, so the question is, will the curvature be constant? We're about to see. All right, so now, what do I need? The magnitude of that? You want to do that now? So I'm just kind of looking over here like, what am I trying to get, right? So let's do the magnitude of that. The magnitude of the derivative crossed with the second derivative should be the square root of the sum of the components there. So 2 squared plus negative 2 squared plus 0 squared, which just square root of 8, root 8. Okay, that's going to be my numerator, right? Okay. Now I need the magnitude of the derivative cubed. Let's figure out what that is. Oh, well, yeah, we can do it. What's the magnitude of the derivative?
2 plus 4t squared.
Yeah, you're going to do this squared, right, plus this squared, which is 1 plus 1 plus 4t squared. But all of that needs to be to the third power, right? Because I'm trying to get this together right here, this denominator. I didn't need to do the cube, but I went ahead and did it right now. Good? And that's just 4t squared plus 2 cubed. I'll leave it like that. That's fine. You could, if you want, do this to the 3 halves. I mean, if that makes you happy, you could do that as well. It means the same thing, right? So I've got all the pieces. Now I'm ready to go ahead and tell you what the curvature is. The curvature of this is this up here, root 8, over this here, and I'll write it with the root. 4t squared plus 2, all of that cubed. This curvature is not constant. Do you all see this? This curvature depends on what? T. So as T changes, the curvature changes. So as you're at different points on the curve, you have different curvature. Can you tell from that formula that the bigger T that T gets, the smaller the curvature gets? Right? Because your numerator is a constant, right? So the bigger the T gets, the bigger the bottom gets, the smaller this ratio gets. So whatever this graph looks like, whenever you get further and further into time, I guess you could say, you should get less curvature. Now this is not the picture. Is that the picture? No. Thought I had the picture. It's 3-dimensional. That's not it. I don't have the picture. I guess we could go to GeoGebra and graph it. Do you know how to graph vector functions in GeoGebra? I know some of you do. I'm going to show y'all because it's pretty cool. You can use this to check some of your answers, in fact. Oh, the internet wasn't working earlier. Let me see if it's working now. Looks like it is. Let me erase this. So we had for a vector function, we go to 3D graphing first, not 2D, 3D calculator. We go to the input and we do just a parenthesis. And then we use the variable t. And what was it? It was t comma, our original vector function, t comma t comma 1 plus t squared. There it is. So this is it. It's just, what is this thing? It's just a parabola, but just kind of at an angle, right? That's going really fast, kind of making me dizzy, but that's it, right? So if t is 0, right? Where are we at t equals 0? Where are we? 0, 0, 1. We're here, right? Now, start the clock, right? T goes, and now you're going to start moving, right? You're going to start moving. When you start moving, right, in the beginning, your curvature is pretty big because you're at this bottom of this curve, right? Pretty tight curve. And then as you go on, what's happening? You're still curving, but it's not as much, right? Well, that curvature formula that we found measures how much that curve is, how much that curving is. That's all. I really just wanted you to see how to type this in, all right? How would you type in a plane? X plus y plus z equals 1. There's a plane, right? Cylinder, x squared, squared plus, let's say, z squared equals 9. There's a cylinder. So there were some problems. I know we did it, right? It was like, find the intersection of a plane and a cylinder. You could come here, and then when you get your answer, you could type that in, and you could check to see if your curve is, in fact, that intersection. So it's a tool that I wish I would have had that when I was in Cal 3. I mean, to be able to check your work like that, yeah.
So let's say that we just choose some random number to be t, 3 or something.
Yeah.
And we get our number.
Yes.
What exactly does that mean for the curvature to be let's say 9? Does that mean that it's curving?
It would be you would be interested. I guess you could look at it two ways. If you're comparing the curvature at that point in time to a different point in time, then you'd be able to tell if it's more of a curve or less. But the number 9 wouldn't really mean a whole lot. You know what I mean? It's not like 9 feet. We all know what 9 feet is. A curvature of 9 doesn't necessarily register to us what does 9 mean? Or is that what you're asking?
Yeah.
Yeah. All we know is that the bigger the curvature is, the tighter the turn is. All right. Let's move on. I believe that ends it for the notes for 10.8. And now we're getting chapter 11. I told you we would get into new material today, right? Functions of several variables. Let me make this a little bit bigger. I feel very close to the board. I'm just going to kind of come over here a little bit. There we go. That's a little better for me. All right. So we've already talked in this class about equations, right? Equations that contain x, y, and z. And remember that boring day, well, I said it was boring, where we just looked at a bunch of surfaces, right? And we're like, oh, both the x's and y's are squared, but the z's not. And what does that look like? Those were called quadratic surfaces. And those were equations involving 3 variables. Equations involving 3 variables. Just like if I were to write this on the board, back in college algebra, is that an equation with 2 variables? Back in college algebra, yeah? That's an equation in 2 variables. So when we graph that back in college algebra, that's a line. And one thing we do in college algebra when we see something like this is if you can solve for y, then what we do is we replace the y with f of x. And we say, okay, you know what? The y value is actually a function of x. If you give me x, I can tell you where you are on the line, right? So equations of 2 variables in college algebra, if you can solve for one of the variables, then you can replace that with f of x and rewrite it the same way. And now when we graph it, we can talk about this thing called the vertical line test, right? Oh, that's not right. Should be up one. But you get the idea, right? Here, what we've said in this class is, yeah, if you give me an equation with 3 variables, I can graph it, and we get these surfaces. But if it's possible to solve or isolate the z in that equation, then z can be looked at as a function of the x and y. So if someone gives you the x and the y, then we can figure out what the z is. And when we can do that, we will write it this way. We will write z is a function, and now we have two inputs instead of one. We have x and y. So your z value is determined specifically by your x and y. So here's, let me get my 3 space here real quick. That's x. This is y. So what this is saying here is that if somebody gives me the x and the y, and then you can determine the z from that, right? Give me x, give me y, the z can come out. The z is now a function of x and y. We do have something like a vertical line test here now, because if I give you an x and a y, there can only be one z that comes out. You can't have two. And that's why, like, an equation of a sphere cannot be written like this. Just like back in college algebra, the equation of a circle couldn't be written as a function because you would have fail the vertical line test. So this is it, one input, one output. Just keep in mind that the input here is not a single number, right? What is it? You could argue really that the input is a what? An ordered pair, right? Your input is an ordered pair. Your output is a point on the number line. So, pardon me?
Similar to parametric.
Similar to parametric, but parametric was, you had an input was t, right? And then your output was like an ordered pair or an ordered triple. This is different. So what we're saying here is that this is a function that goes from two-dimensional space into one-dimensional space. The input, right? The input is an x and y. The output is your z, right? So you take your two-dimensional point, you spit it into on a number line, but we can visualize it in three-dimensional space, right? We can say, here's your input. Your input is this plane. Your output is how far up you are and down. All right, continuing. This is what we just basically said, right? So your input is ordered pairs. They're going to be plugged in the function. Our domain is R2. The range is a number. So to be able to visualize this, we'll need three dimensions. All right, so this is just to make sure we understand the basic idea. So look at that right there. If I define a function f of x, y to be equal to the square root of x plus y plus 1 all over x minus 3, then first let's just make sure we know how to do part A. All we're doing there is replacing what with what and what with what? X with 1 and y with, x with 2 and y with 1. Right, so this would be square root of 2 plus 1 over x was 2. 2 take away 3. Negative 2. Okay, so what this means is that if you plug in the point 2, 1, so go on the x-axis 2, the y-axis 1, your answer is what? Negative 2. I go down 2 and I put a dot there, right? Okay, let's try 0, 0. What's f of 0, 0? 1 over negative 3, or is it negative 3? Yeah, negative 1/3. That means that if I go x 0, y 0, so if I'm at the origin, then the output is just go down 1/3, right? So I have a point right there on the z-axis, just, yeah? Okay, so I've got 2 points so far. Out 2, over 1, I was down. And then at the origins, down 1/3. Okay, what about negative 4, 1? What do you get up top? Yeah, you get imaginary number, don't you? Over the bottom is negative 7. Square root of negative number, right? So you have i's. How do we deal with i's in this class? We don't, right? We don't. I already told you all that. This is not a class, does not involve imaginary numbers. That would require 2 more dimensions, and we're done after that, right? So this is undefined, right? That means it's undefined. The function is not defined here. There's a domain, right? There's some things we can't plug into this function. The function's going to have some problems, right? So let me just try and visualize again what just happened. We tried to go, x is -4, so we tried to go back 1, 2, 3, 4, and then y-axis was 1. So coming on the y, we came over 1. We tried to plug that in, and this function doesn't know what to do with it, right? So there should be no point above this or below this. And there's probably more places where that happens, right? So that's the next question. Can we determine the domain of this? Yes?
Your domain is x plus y must be greater than or equal to -1.
Okay, yes. So for domain, right, part D, we're saying let's talk about what would screw this thing up or what makes it okay. We have a square root, right? We need to make sure whatever's underneath the root has to be what? Can it be 0? You can take the square root of 0. So for domain, right, for the domain of this function f, the first thing I know is that I want x plus y plus 1 to always be greater than or equal to 0, right? Like I need to make sure that whatever is underneath the root, what do we call the thing underneath the square root or any root? Radicand. It's called the radicand. The radicand, we need the radicand to make sure it's always non-negative. You can say it that way, right? Non-negative means 0 or positive. Okay, that right there is a linear inequality. So what I'm going to do is this. I'm going to isolate y. Just subtract x, subtract 1. And now comes the question, have you ever seen something like this? Do you know how to solve this? Depends on your background, right? So I'm going to remind you or show you for the first time how you go about solving this. What we do first is we turn it into an equation. Okay, we turn that to an equation and I graph that line. That's a line, right? I'm going to just graph it. You all know how to graph that, I hope? Negative slope of 1, or -1 is your slope, y-intercept is -1. So if I go -1 on the